Welcome. Today we're going to take a look at Dijkstra's algorithm. Dijkstra's algorithm is an absolute highlight. It's simple, it's elegant, it solves a natural problem for which there is no obvious solution, and that is the shortest path problem. The shortest path problem is a problem on graphs, and here you see some examples of graphs. The type of graph you can think of today is, for instance, a road network. And in a road network, we often want to find a fast route from A to B, and that corresponds to solving a shortest path problem in a graph. So let's start by reviewing some graph terminology. A graph is a pair consisting of a set of vertices, V, and a set of edges, E, where the edges are pairs of vertices. And depending on whether we see these pairs as unordered pairs or ordered pairs, we have undirected graphs or directed graphs. And the type of graphs that we're going to look at today are directed graphs, but you can use shortest path algorithms just as well on undirected graphs. So, and we are interested in shortest path. So what is a path in a graph? A path is a sequence of vertices such that between consecutive vertices I have an edge. So here you see examples of path, and if I'm in the setting of a directed graph, then I also have to have the edges in the right direction. And a vertex V is reachable from U if there's a path from U to V. And today we're going to look at graphs where the edges have weights. So for every edge I have an edge weight, and you can think of that as the distance between those two vertices. Or you can think of it as a travel time in the setting of road network. And then the length of a path is the sum of edge weights along that path. And if you simply take weights 1, then that corresponds simply to the graph distance, so the number of edges along the path. And then the distance between two vertices is the length of the shortest path. And we set that to infinity if the vertex V is not reachable from U. So distances and shortest path are what we're interested in today. Let's formalize the computational problem that we're going to solve. We're going to solve the single source shortest path problem. What does that mean? The input is a directed graph with edge weights, and we're going to assume that those edge weights are non-negative. So if you think of road networks and as edge weights travel times, then those naturally will be non-negative. And additionally, as input, we have a starting vertex S. So S is our source. That's why we're saying single source, because we're computing the shortest path from S to all other vertices V. So the output will be for each vertex V, the weight of the shortest path from S to V. So if this, for instance, is our graph, then what we want to have, so here's S, the shortest path to Y, that will have a distance of, or weight of 4. The shortest path to Z will have a weight of 7, for instance. The shortest path to T will have a weight of, let's see, of 5, and so on. Let's see that also as a small quiz. What is the length of the shortest path from S to X? There are several paths from S to X, but the shortest one is this one. And it has first a weight of 4, then a weight of 1, then a weight of 3. So 4 plus 1 plus 3, that's 8. So we want to solve the shortest path problem, single source shortest path problem, and we're going to see an algorithm for that. And for that, let's introduce some extra terminology. SP will be the shortest path distance from S to V. So the weight of the shortest path from S to V. And we're going to store that. So in the algorithm, it will be stored as shortest V. So at the end of the algorithm, shortest V should contain the shortest path from S to V. But that is actually something that at some point then, when we've seen the algorithm, we will want to prove that that's indeed the case. So we compute distances, but obviously very often we actually want to know the shortest path. So we don't only want to know that there is a route from A to B of a certain length, but we also want to get that route. And for that, we are also going to store predecessors. So for a v, we're going to store the predecessor on the shortest path from S to v. So for instance here for x, since we're going from S to y to t to x, the predecessor of x, that would be t. And for S, we are going to set the distance to 0, so we can immediately reach S from itself, and it will have as predecessor none. And if there is a vertex that is not reachable from S, then that will also have predecessor none, but then as distance infinity. So let's see Dijkstra's algorithm, and I'm going to show it by this example. We start by setting all of the shortest values, so shortest of v, to infinity. And that corresponds to the distances to those vertices, at least the distances that we currently know about. And because we haven't explored any path yet, the best distance that we know about is infinity, except for S, because S is simply reachable by itself using the empty path. So S gets a 0, and all of the predecessors, those we set to none, because so far we don't know about any predecessors yet. Now we take all of the vertices and put them into a queue, and we call that queue. And as long as there are vertices in that queue, we always extract the one with the lowest shortest value. So initially all of the values are infinity except for S, which has a value of 0. So S will be the first one that we're going to extract. And then we're going to look at the adjacent vertices. So adjacent means there's an edge from U to V, and we're going to relax the edges UV. So what does relaxing an edge mean? Let's take an example here. So the first adjacent vertex will be T. Now we are currently processing S as U, and we know that we can reach it with a distance of, in this case, 0. Now I know that I can reach T by going to S. I mean, I'm already at S, and then using that edge. So, and if this gives me a better path than the path that I currently know about, and I currently don't know about any path, then I'm going to store that distance, and that is relaxing an edge. So let's see that. If shortest of U, so that's here in our example 0, plus the edge weight, so 6, 0 plus 6, if that is smaller than the current value that we have, infinity, 6 is smaller than infinity, yes, then we're going to set the value to the value that we just computed, so 0 plus 6. And we're going to set the predecessor of T, or more generally of V, to U, so in our case, the predecessor of T to S, and I'm going to show that with this arrow. So now we're done processing the edge from S to T. Now we look at whether U has more or S has more adjacent vertices, and that is indeed the case. So we have Y. Again, we relax the edge, and because 0 plus 4 is smaller than infinity, now Y as a distance gets 4. And the predecessor again is S. Now we are also done with 4, and we have completely processed S. So for S, we're now done with the while, and we're with the next iteration of the while loop. Now in the next iteration of the while loop, we're now taking the vertex in the queue with the lowest shortest value. So S is outside of the queue, that's why I'm drawing it black. The lowest value that I currently have is a 4. So Y takes the role of U. So now I'm going to look at the adjacent vertices of Y, that is, for instance, Z. We're going to relax the edge Y to Z. Now I know I can go to Y with a distance or path of length 4. If I then use that edge, I get a path of length 7. That is indeed smaller than infinity, so that's then the distance that I now take for Z. So I update the distance for Z, and as predecessor, or at least current predecessor, I'm going to take Y. So the predecessor of Z is Y. Now, we are done with processing z as adjacent vertex to y. Now we have also x. X currently has an infinity, so 4 plus 9 is definitely smaller. That is 13. So x gets a distance of 13 and y as predecessor, at least so far. Now we're done with the 13. T is also reachable from y with a distance of 5. We're going to update the predecessor to y. So previously the predecessor of t was s, because that was the first path or the first edge that we relaxed for t. But now we saw that there's an even shorter path. And so I had a 6 here, but now I saw, because I have a 4 here and a 1 here, that with 4 plus 1 I have a shorter path than the path of length 6. So that's why I updated the distance and I updated the predecessor. Now I'm also done with that edge, and I am done with processing y. So now y is also outside of the queue. We're left with t, x, and z. We again take the one with the lowest value, that is t. We're going to relax the edges. T has an edge to y, but of course we already have the shortest distance computed to y, so we won't be able to relax the edge from t to y. Then t also has an edge to x. So now we have the case that so far the best path that we had for x had a length of 13, but via t we can get a path of length 5 plus 3, so 8. So we're going to update the distance to x to 8, and we're going to take t as predecessor. So we successfully relax this edge. Now we're done with t. Z and x remain in the queue. Z has the smaller shortest value, so we're going to process z. Z has as adjacent vertices s, but s obviously we won't relax the edge from z to s, because s we already have the shortest path. Then there's x also, but also for x going via z gives me 7 plus 5 is 12, that's more than 8, so we're not going to relax that edge. Now we're done with z. The 8 remains. For the 8 obviously there's nothing to do, and we're done with the algorithm. So now, assuming that our algorithm is correct, these values are the shortest path lengths from S to those vertices, and we also have the shortest path by following the predecessors. So what we see, for instance, from S to X, there's a path of length 8, and it is the path following those black arrows. Let's have a small quiz, and that is the following. While I was running the algorithm, how many edges were relaxed successfully? So how often did I go into this if case? The correct answer is 6. And which edges were those? So obviously the black edges, so the ones that I'm here showing as predecessors, we set them as predecessors within the relax. So those have to have been relaxed. But also, if you remember which other edges we relaxed, it was initially from S to T, that edge we relaxed, and we had a 6 at some point here. But also the edge from Y to X, if you remember, there was a 13 at some point here, and that came from that edge. So we have 6 edges that we relaxed. But for instance, let's say the edge from Z to S, that was not relaxed because 7 plus 7 is larger than 0. We have the algorithm. Now let's look at correctness, and let's then look at the running time. And the correctness can be proven using the following invariant, and it simply states that for all of the vertices that are no longer in the queue, so the vertices that are black in my examples, for those the shortest path distances have been computed correctly. So shortest V corresponds to the actual shortest path distance. So we know initially this is not true for most of the vertices because infinity is just an upper bound. But what we're saying is that as soon as a vertex has turned black, so it's outside of the Q, then we have those distances correctly. In terms of termination, so what we get at the end, it then indeed means that we've computed all of the distances correctly because at the end everything is black. Also, initialization is easy because initially this is true even when we have S outside of Q. So for S, the 0 is correct. So the interesting part here is the maintenance. And let me have as an example this graph here, but let me simplify it slightly so to make the example simpler. To be able to use this example, I have to introduce a small error in that example, and that is this 15 here. Now, we want to do a proof by contradiction. And what does that mean? It means that we assume that maintenance at some point fails, and we lead that to a contradiction, and then we know that maintenance cannot fail. So let's assume maintenance fails for V. So when we take V out of Q, that is the point where maintenance first fails. So that means, so what does it mean that the maintenance fails? It means that then shortest of V is not the shortest path distance. Now let's consider the actual shortest path from S to V. So let's call that U1, U2, U and so on. And so let's take it as an example. So let's say X, let's say that would be our V. And then we call that UK in our case. S, that is U1. And UI is the first vertex on that path that is not outside of Q, so that is in Q. In our example, if you look at the actual shortest path, which goes like this, it would be T. So T would be our UI. And it would be U1, U2, so I is 3 here, and K is 4. And so first of all, there are always vertices that have been removed from Q because at least S is already removed. Also, there's always an element that is still in Q. In doubt, it is the element V because we do this just before removing V. So it could be that UI is indeed equal to UK, so equal to V. But in my example, they're different. Now, let's look at how we can lead this to a contradiction. So we know that for V, this equality failed, and the distance, so shortest of V, then has to be larger than the actual shortest path distance, because shortest of V always corresponds to the length of an actual path. So what we have is that the shortest path distance from S to V is smaller than the shortest of V. Now, shortest of V was the one that I'm next removing from Q. So it will be smaller equal the shortest of any other element that is still in Q, so in particular of UI. So shortest of V smaller equal UI, and that's why I had to manipulate this example to put a 15 here, because otherwise X would not be the next one that I take out. And again, maybe this one doesn't exist, then, or it does exist because in doubt it's simply V. So it could also simply say shortest of V smaller equal shortest of V. That would be fine. Now, for UI, we do actually have an upper bound on the shortest of UI because we know that UI minus 1 is not in Q. And when we took UI minus 1 out of Q, we relaxed the edge from UI minus 1 to UI. What does that mean? It means that we know that shortest of UI is smaller equal shortest of UI minus 1 plus the weight of that edge. Because we did definitely try to relax that edge. And we do actually know that this shortest value corresponds to the shortest distance, so the length of the shortest path from S to, so what I want to say here is 2ui minus 1. Now if I look at the shortest path from S, from u1 to uk, then the length of that simply corresponds to adding up the edge weights of the edges on that path. Now what we have here are some of the edges of that path, not necessarily all of them, but some of them, and for those the edge weights. So this sum is definitely smaller equal the actual shortest path length from S to V. And that gives us our contradiction, because what does it say here? We're saying the shortest path from S to V is smaller than the shortest path from S to V. So I have the same quantity and we're saying it is smaller than itself, and that is our contradiction. So we know that our initial assumption was wrong, so we know that the invariant didn't fail for V, and therefore it is maintained correctly. Now that we know that the algorithm works, let's take a look at the running time, and that's actually quite interesting. So we have the algorithm here. We will denote by n the number of vertices, m the number of edges, of course m smaller equal n squared. Let's take a look at step 1. So first we do something per vertex, and that's constant amount of work per vertex. Overall that will be linear in the number of vertices. Here we do something for one vertex, again for all vertices. Overall theta of n, so linear in the number of vertices. Step 2. So here we insert everything into the data structure Q, but we don't know what Q yet is, so we didn't specify that, so we don't know how long step 2 takes. Then we have the while loop. So in the while loop we have to be able to find the element with the lowest shortest value still in Q, and then we call relax, and we do that per edge once. So we call relax n plus m times, but also we don't know, so first of all we don't know how efficiently we can find the vertex with the lowest shortest value, and we have to be careful also here, because here in relax we update the shortest value, and that obviously also influences step A. So we know some of the running time, but we don't know how long does step 2 take. We don't know how long does it take to find the vertex with the lowest shortest value, and the bookkeeping that we need to do for relax when we update the shortest value, that we also don't know how long it will take us. Now let's take a look at what abstract data type we want to have for Q, and probably you already guessed it. So let's see which operations we need. We need to be able to insert elements into Q. Then we want to be able to extract the element with the lowest shortest value. So if shortest is my key, I want to be able to extract min by the key shortest. So if shortest is my key, what I also want to be able to do is I want to be able to change the key. But when I change it, I only need to decrease it, because in relax, if I change it, then only because the new value is smaller than the old value. So I also need decrease key. And what does this correspond to? This corresponds to a priority queue. So what we want to have is a priority queue, and then in terms of these operations, the algorithm would read like this. So we call insert for every vertex, or we can also simply build our priority queue. Then we have here the extract min, and then if necessary we decrease a key. Now we need to select a data structure for our priority queue, and that is less obvious than you might think. So let's start simple. Let's assume we do something trivial. So we use an unsorted array as a priority queue. So in an unsorted array we can insert, we can find the minimum, and we can also decrease a key. So let's make this a quiz. if I want to extract the minimum out of an unsorted array of numbers, how long does that take? So that takes linear time, because the only way to find the minimum is to scan over the array. So if I use an array as implementation of a priority queue, what I get in terms of running time, so it's easy to insert an element. I can do this in constant time, or if I take into consideration that I might need to grow the array, then this is amortized constant. Extract min, as we just said, takes linear time, and then decrease key, if I already have access to the key, I simply need to change that number. I can do that in constant. Now let's plug this into Dijkstra's algorithm. So we implement the priority queue now as an array. So how long does that then overall take? So insert, I can do constant time per element. So then this will be linear time. Extract min, I will extract every element once, and that takes me linear time per element. So that will be actually quadratic time. So if I count more carefully, I will get the sum I goes from 1 to n theta of I, but also that is an arithmetic series that is also quadratic. And then the decrease key, I call that for every edge once, and it takes constant time, so that gives me a theta of m. So the bottleneck here is extracting the minimum. That takes quadratic time, meaning that Dijkstra's algorithm, if I use an array as priority queue, takes quadratic time. Let's try to do that better. And the better option might be, or hopefully is, a heap. In a heap I get all of these operations in log n time. And as a quick reminder, what is a heap? So here you see a heap. We can store it in an array, and we have this min heap property. So a parent is smaller equal, or has a key smaller equal than its children. And there will also be a link to the video on heaps if you want to take a look at those again. Now with all operations in order log n time, what is our running time? So, okay, to be precise, the insert, there we can simply do build heap, so that if we want to, we can do that in linear time. Extract min takes log n time, we do that n times, so that is n log n. And then for every edge, we might need to do decrease key, so that is then m edges. For each of those, it costs me log n time. So why log n and not log m? Because I have in my heap, not the edges, I have the vertices. So the heap has size n, so it's log n, but I do it per edge, so m times log n. So with a queue implemented as a heap, I get n times insert, so n log n, or if I want to, by using build heap, linear time. I extract n times the minimum, that is O of n log n. I do decreased key m times, that is O of m log n. So Dijkstra's algorithm overall takes order m log n time. And that means it works well if our graphs are sparse. So if I have, let's say, only a linear number of edges, which for a road network is very realistic, then this is an algorithm that runs in n log n time. So that is extremely fast. If I have a large number of edges relative to the number of vertices, so m could be quadratic. So if m is quadratic in n, then actually this is n squared log n, so it's even worse than an array. So what we now have is that for sparse graphs, a heap is better, and many graphs are sparse, but there are cases where a heap does not work that well, and the reason for that is the m times log n. So it's a natural question whether there is a data structure with which we can avoid it, and there is a data structure. So one such data structure is called Fibonacci heaps. I'm not going to show them here and now, so they are somewhat more involved, so they would warrant their own video. And the running times that we get for that is for insert and extract min, log n, so that gives us n log n. But decrease we can do in amortized constant time. So not in log n time as for a min heap, but in amortized constant time, and that gives me O of m for all of the decrease calls. So using Fibonacci heaps, Dijkstra's algorithm runs in O of n log n plus m time, and that's as good as it gets. Let's wrap up. We've seen Dijkstra's algorithm, an algorithm to solve the single source shortest path problem for graph with non-negative edge weights. And it runs in the running time just mentioned if we use a Fibonacci heap. In practice, you will probably not want to use a Fibonacci heap because the constants involved in the running time are quite high, and it would be better to simply use a min heap. So that works quite nicely, and then Dijkstra's algorithm is a very practical algorithm. It's also a very simple and elegant algorithm that was invented by Edgar Dijkstra already quite a while ago, 1956, over coffee. It is an excellent example of the use of data structures in algorithms, so using a min priority queue in an algorithm, and depending on what data structure I use, I get different running times, and it's actually quite deep in terms of how to choose the optimal data structure. When we want to do route planning, then actually at the core there's Dijkstra's algorithm, but we will not want to run it from scratch, because running it from scratch, I mean n log n plus m, for where n is a number of vertices in our road network, obviously is too large. So what we're going to, or what is used in such systems, is there are data structures where you, for instance, pre-compute certain distances and use that to then answer the route planning queries quickly. So that is actually kind of a very interesting research area with many clever data structures, a lot of interesting practical algorithm design, but still at its core, Dijkstra's algorithm is used quite a lot, for instance, when computing those data structures. So that's all about Dijkstra's algorithm. See you next time.